Exercise 741. This is the only one in this section, and it starts off like the two results that we have seen in this section, with an absolutely convergent series of real numbers, summation an. But unlike those two results, now we don't have a bijection. Instead, we simply have an increasing function. That of course means this: f of n plus 1 is greater than f of n for all natural numbers n. But still the conclusion is like before, this series is still absolutely convergent. That we have to show. And a hint is also given. The hint asks us to try to compare each partial sum of this series with a partial sum of the original series. Slightly different is mentioned because it's different than the usual thing. We are, however, not going to follow the hint exactly. We will do something else. So let us now see the solution. Actually, we are going to follow the argument already given in the proof of proposition 741. That is the first result of this section. And in fact, I will not supply all the details. A gap will be there that will be left to you. So we are saying that we are not going to follow this hint exactly. That just simply means that we are not going to consider the partial sums of the given series, but instead the corresponding series where we have absolute value. Okay, because this is given to be absolutely convergent. So this is how we are going to start off. Define Sn to be equal to this finite series. Where n of course is a natural number. In fact, this n is variable, you can understand, and that's how you have the nth partial sum of this series. And similarly, we define Tm to be this. And m, like capital N, is also a variable natural number. Further, let L be the supremum of Sn as n varies over all the natural numbers, and L prime be the supremum of Tm as m varies over the set of natural numbers. Okay, now what are we given? We are given that this series is absolutely convergent. That means, by definition, this series is convergent, and that again in turn means, again by definition, that these partial sums Sn form a convergent sequence of real numbers. And also, from the theory of convergence of such sequences which are monotone increasing, we know that Sn will converge to L, which is the supremum or the least upper bound of the sequence. So all these things ultimately mean that L is a real number. So now we write, since we of course are not going to write everything, we will write just simply the conclusion. Since summation an is absolutely convergent, is absolutely convergent, L belongs to R, and in fact L is the sum of this series. Sum of which series? Sum of this series. Now the increasing nature of f of our function, given function f, implies that f is 1 to 1, and this is the key to this solution. This is really what will take the solution forward. In spite of not necessarily being a bijection, it may be a bijection, it may not be, but the increasing nature ensures that f is at least 1 to 1, f is injective. Hence, for any, okay, so what are we going to do here? We are also considering this. So that means for any natural number m, f is a 1-to-1 function of y. We are going to now say what y is. Y is the set of all natural numbers less than or equal to m onto I hope I have considered the correct order, that I am considering f to be a function from this set into n. We will see. If it is not what we are supposed to do, then we can change the order of this onto f of y. Now y an argument similar to the one in the proof of proposition 741, but given that I always forget these numbers, let me just see whether it is really 741. We get L prime less than or equal to L. So it is that thing. If you go back to the proof of this proposition, which is our first result, where we deal with only series of non-negative real numbers, and there we show that any rearrangement does not change anything. I mean, does not change convergence, and also it does not change the sum of the series if the series that you are starting with is convergent to begin with. Now in that proof you will see that the proof of course starts just like how we have started this one, and when we come to the part where we are going to use the function f, there of course we are given that f is bijective and all those things, but ultimately we end up using only the fact that f is a one-to-one function from a set which looks like this onto f of y. F is one-to-one that we can see from here itself. So when you restrict f to a subset of the original domain of f, which is the entire set of natural numbers, the restriction still is one-to-one by properties of one-to-one functions, and because we are considering the image of y itself, so it will be onto, and then after that all the things are exactly the same. So you just have to go back to the proof, and there you need to go through the steps again, and you will see that after that there is no change, and that's it. That will give you this inequality. Of course, in the original proof of this proposition, we do not just simply prove that this series is absolutely convergent, but more than that we also prove that the sum of this series is the same as the sum of the original series. Here however that is not needed. We have been asked to only show that this series is absolutely convergent. So we need only this much, because you see, what is L prime? L prime is the supremum of the sequence of partial sums of this series that I wrote here just now. This implies because L is a real number, so this inequality tells us that L prime is also a real number. And again I am going to repeat something that I clarified while we were proving this proposition, that simply because L is a real number and L prime is an extended real number that is less than or equal to L is not enough to conclude that L prime is also a real number. If just simply two extended real numbers like this are given where L is a real number, that will just let us conclude that L prime is not equal to plus infinity. But still we have the possibility that L prime may be equal to minus infinity. But now these are not just any two extended real numbers, but L prime. This part I would like to again say in detail. You see, L prime is by definition what? This. And what is each Tm? Each Tm looks like this. Where n varies from 0 to capital M. So each Tm is a non-negative real number, and we are considering the supremum of such Tm's. So there is no chance that this L prime can ever be equal to minus infinity, because all the tm's are greater than or equal to 0. So by the nature of L prime is also greater than or equal to 0, and that allows us to next write this implies L prime also belongs to R. But of course we are not going to write these things because these things are there in the background, which when we are writing the proof, all these things should already be there in on our mind. Okay, so that is the full justification for the next line that we will now write. This implies now L prime belonging to R means what? i.e. our this series is convergent, and in fact its sum is L prime by definition. This in turn implies that this series without the absolute value is absolutely convergent, and that completes the solution. Still there is something else. Even after completing the solution, there is something else that I have not in fact talked about in detail. I will address that now. This in turn implies a f of n, where n varies from 0 to infinity, is absolutely convergent, and that is the solution. Now the thing that I haven't really explained is this. I said in one of these lines that since f is increasing, so it is 1 to 1. Exactly how is that true? Say you are given that f is an increasing function, you want to prove that f is 1 to 1. What will you do? You consider two points in the domain. Of course, in this case the domain and the range are the same set. This set and this set, they are the same, such that they are different. Okay, now by definition, if we can prove that this implies that their f images are also different, then f is 1 to 1, and that we can prove using the hypothesis that f is increasing. How? You look at this, you see, because n is not equal to m, one of these two will be true. It's enough to consider only one of them because there is nothing specific that distinguishes the situation between n and m. They are both just some distinct natural numbers. So it's enough to consider this. Now, the condition that we are given, or the definition of an increasing function, is just simply this. It seems that this can be used repeatedly in order to reach m starting from n, like this. You have n, then because m is greater than n, so if you keep on adding 1 to n, eventually after some finite number of steps you would reach m. So what you have to just simply notice here is that you can apply this condition, because your condition for increasing function is in fact true for any n. So in place of n you can also think of n plus 1. You then get fn plus 1 less than fn plus 2, and it will go like this. Eventually you would reach fn, and in fact that itself is the reason for fn to be less than fm, which would imply that they are not equal, and we are done. However, this is not exactly rigorous. I mean, this part, if you just simply write it like this, still it's not absolutely rigorous. To make it rigorous, you have to use induction. But on what variable will you use induction? Let me give you an idea of what can be done. You see, because n is less than m minus n is a positive natural number. On this variable m minus n, you can use induction to get it done in a very nice way, and you don't have to keep one variable fixed and then use induction on the other. I mean, that can of course be done, but there are some problems will likely arise. I cannot point my finger on what is going to arise, what that will be problematic, but this, if you use induction on this, then I think it will be smooth. So what I am suggesting here is that you in fact try to prove that f is 1 to 1 in this way, but of course if you see the thing here, you can see all the steps here except this thing, this part which is a little not that rigorous. So I am asking you to make it rigorous by applying induction on m minus n. So here let me again write exactly what I am asking you to do. So now what you have to do is this. It is given that this f is an increasing function. This is given to you. And the statement that you need to prove is this: for any two natural numbers n and m, you need to prove this: n less than m implies f of n is less than f of m, and I am asking you to apply induction to prove this, and the variable on which you will apply induction is m minus n. So the base case for this would be, because n is strictly less than m, the base case would be this. You need to note carefully that in this base case many things, I mean many different m's and n's will appear. So actually applying induction on m minus n does not mean that we are taking the smallest value of n or the smallest value of m. No, we are at once considering these infinitely many possibilities, 4 minus 3 equal to 1 and so on. You try to do it. If you don't get it, then please let me know. So this in fact completes whatever we had in this section. So let us now also quickly see what we have in the next section. Of course we are not going to do anything major in this video itself, but let us at least see what the next section is about, and let's say state the first result. As I have already said, the next section is about the famous root test and ratio test for convergence of series. So it starts off with just these things. Straight away the results are given and they are proved. So the first one is the root test, and we are going to see its statement. And the section heading is of course this 7.5, root test and ratio test, the root and ratio. Okay. So is it proposition? No, it is theorem. It's too important to be a proposition. Okay, so here we are going to start with again a series. Let summation an, where n is varying from, is it 0? No, here the author has taken m. Actually does not matter, but how we are starting the series, that is what the initial index is. Let this be a series of real numbers and let alpha be this thing. Limit superior of the nth root of the absolute value of an as n tends to infinity. This is a quantity associated to this series. Let me just first complete the statement and then we will see what it means. Now there are parts. If it turns out that alpha is less than 1, then the series is absolutely convergent. Absolutely convergent and hence conditionally convergent. That means just simply convergent. So that is part A. Then part B, if alpha is greater than 1, then the series is conditionally divergent. The term conditionally divergent may be a little confusing to you. It just simply means it is divergent. That's all. And hence cannot be absolutely convergent. And there is a part C also, which of course is about the only possibility left. If alpha is equal to 1, then we cannot conclude anything. I think the actual language is something else. No? We cannot assert any conclusion. Same thing, the meaning is same. Okay, so now what is it? What is it saying? Let us first concentrate on the definition of alpha. You note that we are actually considering a sequence. This is the sequence we are considering. Its nth term looks like this. And because we have 1 over n, so you can understand that we have to consider n from 1 to infinity. Now, technically speaking, there may be a problem because we haven't said anything about what m is, or rather the author has not said anything about what m is here. M is any integer. Now, it is not a problem if m is a non-positive integer, that is m is negative or 0, or even if m is 1, there is no problem. However, if m is 3, for example, then this does not make sense. You cannot start n from 1 then, because a1 does not exist. a1 has no meaning. So it will depend on n, and the reason I cannot take m here is that I am considering nth root, right? So if it happens that m is negative, then I have to consider n equal to 1, and then n increases from there. So you can understand that you may have to change this initial index, the initial value of the index, but that is not really a very big thing. The thing here is that you should note that whatever the real numbers a n are, absolute value of a n is a non-negative real number, and its nth root, where n itself is a positive real number, exists. Okay, we have already proved these things before. We have seen in the section on real exponentiation that for any non-negative real number there is an nth root. So this sequence, there is no problem with this sequence, and the limit superior of this sequence is alpha, which can be calculated, and unlike ordinary limit superior and also limit inferior, they always exist. Now if it turns out that alpha is less than 1, then your series is absolutely convergent, and hence conditionally convergent means just simply convergent. If alpha is greater than 1, then your series is divergent, so of course cannot be absolutely convergent. But if alpha is equal to 1, then we cannot conclude anything. It may be convergent, it may be divergent, and in fact we will provide 2 examples where alpha is equal to 1, one series is convergent, and again alpha equal to 1 for another series which is divergent. So nothing can be concluded in this single case. One more thing that you should note is that alpha is an extended real number in general, because you see, if you recall in the chapter on sequences, we have already seen that even if we consider a sequence Bn of real numbers, its limit superior, of course it will exist, but it may be minus infinity, it may be plus infinity. One of those situations will not occur here. I am not saying anything more about that right now itself, because we are not going to prove it today. But in general, alpha is an extended real number, but even then these inequalities of course hold their usual meaning in the extended real number system R star. Okay, so with that general meaning, we have all these things true. So we will see its proof in the on next Sunday, and we will see the ratio test also most likely. And the proof is not very difficult. In fact, from the definition of alpha, the fact that it's the limit superior of a sequence and the properties of limit superior, limit inferior that we already developed before, from that the thing will just naturally follow. And one more thing is that in this proof, the convergence of geometric series will play a role, which is the kind of series whose convergence we have already seen, and which is something elementary. And geometric series, and infinite geometric series which is convergent, is in fact arguably the first kind of series that we encounter. We encounter for the first time in life. Whenever we are introduced to infinite series and their convergence, almost always it's the geometric series. So with that, I am ending this tonight. If you want to say something about this, positive, negative, or any thoughts, anything, you can use the comment section below, or you can mail me at my usual address. The link will be there in the description. And the next video will be on Tuesday, of course. So we have in fact already gone through calculus once more, right? So that means the next is going to be what? Group, fields, vector spaces, calculus, number theory. Okay, let's do number theory this Tuesday. So that being said, I will wrap it up for tonight. So see you on Tuesday with number theory, where I think we are right now solving some exercises based on Euclidean algorithm to calculate GCD. So that's just it. So see you on Tuesday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.